The title of the talk is Testing of the Photovoltaics, an assessment of where we are and where we need to go. Pretty lofty title for what I'm going to be doing, which is essentially an update on the standards activities relating to the testing of PV for long-term durability. So with that, let's go with our overview, which basically says that with the rekindled interest in renewable energy, you're also seeing a revitalized activity level in the standards writing organizations that deal with the testing of PV. So we're going to be discussing a little bit about the importance of weather durability testing, conduct an overview of some of the more important PV standards out there, and discuss their stated purpose and the limitations that they may have, and then update you on some of the trends that we see in the sphere, and then talk about some alternative approaches to PV testing as well. So, why do we test? Atlas has been around for 100 years, and we are the primary provider of services and instruments for testing materials, especially for durability. And the whole purpose of this is to help customers around the world provide the most reliable and durable products. When we do that, we help them to minimize the financial liability of early product failure. There have been some very famous cases of the tremendous costs associated with early product failure, like I'm showing here. Ford Motor Company, even though my friends from Ford remind me every time I show this slide that they were not the only ones. So just to say, Detroit had a very severe issue with paint peeling, and that resulted from the carrying over of one test methodology that was suitable for a certain technology of paint to a more modern painting technology where the test was no longer suitable. And this resulted in the passing of materials that should not have been passed. And the ultimate result of that was a tremendous amount of failure of paints on cars coming out of Detroit. That, of course, costs in the billions of dollars. Likewise, we've had situations in the stadium for the Tampa Buccaneers football team where the red seats, Tampa color, changed to pink in no time at all. This, of course, resulted in having to change all the chairs, which I was told cost about $2,500 per chair. So you can imagine a stadium full of chairs was quite a cost to pay for early product failure. Again, because inadequate testing was done. Well, we have the very same issues in the PV industry. Early product failures are likely to cause a tremendous liability on the companies, but even more than the examples that I've just talked about, because early product failure for PV module is not just a cosmetic issue. In fact, it can relate to significant safety and performance issues, which would only lead to increased liability exposure that a company would have. So therefore, the long-term durability testing of PV modules is even more essential than it has been for the traditional worlds that Atlas occupied and helped the manufacturers of products deal with. So PV long-term performance is critical, and PV modules are high-tech, they're expensive, they are required to last at least 25 to 30 years to be financially viable, and they must be safe for their entire life. If they are not, they can be, as I mentioned before, quite a hazard to users and people who casually interact with the PV modules. So therefore, they must be tested in order to meet the criteria that I've listed here. Now, when you look at the importance of durability, you also, as I alluded to, have to consider the financial concerns. Industry experts, even though PV modules have fallen quite a bit in cost in the last number of years, they're still quite expensive, and they still have to last for about 25 to 30 years. The high initial costs of PV modules are typically amortized over the life of the module. So obviously, therefore, the longer life you have, the more equitably, and you can spread out the costs to be manageable on a per annum basis. In the industry these days, bankability is on the lips of everyone. Everyone is talking about bankability, and quite frankly, there are different meanings or definitions of the word out there. When I speak of bankability, of PV or anything else, I am alluding to the investment worthiness of that particular product. So if a PV utility project is bankable, it means that it is worthy of attracting investments from banks, insurance companies, and such. So PV bankability, of course, is a function of reliability. The cost of reliability is significant to module suppliers, and these days module manufacturers need to set aside a certain portion of their anticipated revenue to service warranties, and that is based on the expected failure rates. However, in today's world, where it's a great challenge to determine the failure rates with any sort of degree of confidence, you find that the PV manufacturers have really varying approaches to establishing what these failure rates may be. So what they do is they overestimate typically, and they set aside quite a big portion of their revenue stream. And as such, because they have not been doing a very good job of estimating failure rates and long-term durability, they've had to liberally replace modules that have failed in the field. Of course, going forward, this is unsustainable. You can't maintain this kind of a practice open-endedly. It will drive any company into bankruptcy. So the true warranty costs are not being tracked, is what I'm saying here, and this, of course, threatens profitability. PV bankability is also a function of durability. Now, the common calculation of PV costs is usually looking at the upfront cost, the cost of actually purchasing the PV modules, minus whatever government incentives are out there. In this very simple calculation, durability is very often overlooked. And even when it's not overlooked, it's typically done by factoring a 0.5% per year degradation, which may not be adequate, and because it certainly, for one, does not include any catastrophic failure. So the internal rate of return is very sensitive to the module degradation rate. And because module degradation has a substantial impact on IRR, it should be a critical concern to investors. Investors should pay more attention to having a good handle on the degradation rate and what that is going to do to the IRR before they make investments. So, to summarize, the PV commercial imperatives, as I call them, are based on safety of the modules over their entire life, performance level, the performance that will guarantee an adequate generation of electricity over the lifetime of the modules, and thereby guaranteeing a decent rate of return to investors. And of course, reliability. If you don't have a product that is reliable, you don't have a product that is generating electricity and income. And it doesn't take a stretch to see that durability impacts all of the three that I've mentioned. If your product is not durable and it starts to fall apart, it will be unsafe. If it's not durable and it starts to impact, it will start to impact performance. And if it's not durable, it's likely to impact reliability. Not necessarily, but very likely. Now, I mentioned the terms durability and reliability a number of times, and I'd just like to spend a moment to decouple these terms, which are often interchangeably used, especially in the PV industry. A lot of the instances where the term reliability is used in the PV industry, it is really durability that they mean to the concept of durability that is really being addressed. So let's look at a very, very simple graph, which I think will assist in decoupling these concepts. Reliability, in very general terms, is an analysis which is concerned with measuring discrete absolute failures. If I have something that has failed, it has proved to be unreliable. Reliability, or the engineering term reliability, is concerned with the measurement of what happens when a product fails outright. Durability, on the other hand, involves the route to failures, the mechanisms that change, the property rate of change, which means the kinetics, or the degree of robustness, etc. That is generally more gradual than discrete reliability failure. Now, a durability change may ultimately and often leads to reliability failures of reliability, but not necessarily so. You can see modules like that ugly one I showed a couple slides ago that show obvious signs of degradation, and yet in some instances they've performed beautifully. They have not failed, so they are still reliable. So I hope stepping back and explaining these differences will help deconvolute these terms in your mind. When it comes on to PV durability, a product that spends its entire service life in the harshest of environments, exposed to the most direct sunlight available, and in the process is subjected to rain, high humidity, high temperatures, and so forth. When you speak, therefore, of PV module durability, you really are talking about weather durability. And weather durability, as defined by ASTM, is shown here. In weather terms, it is a measure of the retention of original condition and function of a material after exposure to a specified set of weather conditions. So, really and truly, you're talking about weather durability when you're speaking of durability of a PV module. I've used this slide in another of my presentations, and just to show you that when you are testing PV module and its components, you're really concerned with a number of different types of tests, because the tests that are required as you go through the value or the development stage of a PV module are different. You're asking different questions of the PV component or material or cell or module. Therefore, you have different tests to ask these questions. At the materials level, you'll be looking at screening and selection issues. Cells, you'll be looking at design and process validation issues. At the PV module, you'll be looking at qualification and certification issues. And of course, at the array level, you're looking at issues related to whether my product is going to last over the 15 to 30 year time frame that it is expected to. The testing, as I mentioned before, the different stages of the validation process are different. The tests at the materials level is typically done in a weathering type of instrument shown here, where you can test coupons or small mock-ups of coupons on substrate or super substrate, and those can be done, as I mentioned, in a weatherometer type instrument. In a cell where you have more a 3D type component, you could test that in a flatbed instrument, as is shown here. Of course, PV modules are tested in larger instruments where you are also able to do qualification and safety tests and measure things like IV curves and Pmax, and as well as looking at some aging and hotspot issues. Just a very quick look at the various instruments that are available for testing PV modules. You see on the top left a large chamber for doing solar simulation testing. Again, we've talked about some of these other devices before, like the weather instruments. Corrosion, of course, is a very big deal for PV modules, and that's done in an instrument in the bottom left of the slide here. And I won't spend too much more time on that. There are really very large-scale PV module testing devices, such as are shown here, that in some cases are capable of testing more than one full-size module. And they are usually equipped with solar simulation light sources that meet the requirements of IEC TC82 Working Group 2 and IEC 61215, and these are, as I mentioned before, for testing and qualifying full-scale modules. Okay, so we talk about the different types of testing that's required at the different development stages of a PV module. So let's now look at some of the standards, the testing standards that look at the testing at the different stages that are required in developing a PV module. First, I'd just like to say that, standards get a very bad name, and some, including me perhaps, are not a big fan of the standards writing process because it can be so slow, and many believe that at the end of the day, because it has to incorporate everyone's needs and wishes, that the standards therefore necessarily appeal to the lowest common denominator because it takes everything into account. Now, they really are necessary to address the safety issues we talked about, quality issues, and durability issues. And in the end, they're necessary to assist in the communication between entities, between countries, and so forth. If you're doing IEC 61215 in China and doing IEC 61215 in the US, if you just communicate that fact, then both parties will know exactly what tests your product had undergone. So that's what I mean here when I say it helps to address user confidence and to facilitate trade. Now, the IEC 61215 and 61646 qualification tests are for the crystalline silicone and the thin film technology respectively. And I think the issues with the IEC 61215 and 61646 are well documented. It's more understood broadly these days that these tests are not meant to be long-term durability tests. A few years ago that was not the case. People would say, yes, I know my material can last for 15 to 20 to 25 years because I successfully tested to the 61215. The 61215 was never meant to test for long-term durability issues, just for the early infant mortality stage of your bathtub lifetime curve, which I'm showing here. It was never meant to test the wear-out period over the lifetime of the material. And so there's a broad acceptance of that fact, and now organizations that are concerned and all the stakeholders are getting together and says, all right, now how do we address the fact that the test that was assumed to be providing long-term, address the long-term issues, is now seen as not doing that. So I say here that the need to develop true weather durability tests is being recognized by standards organizations, and that starts out with the solar ABCs. I'll tell you a little bit more about the solar ABCs in my next slide. And the work has been picked up by IEC, ASTM, some certification organizations like TUV and UL, as well as some of the national labs like National Renewable Energy Lab and AIST in Japan. Some private customers of Atlas, of course, are doing their own programs, such as 3M. So there's a lot of activity now to really look at long-term durability testing protocols. So with all of this work going on, the need for coordination is also recognized, because when you don't have coordination, you are going to get overlap, because a lot of the test writing organizations will end up doing things that are being done elsewhere. This will only cause confusion in the industry. In some instances, it will cause double testing. It will delay product launches, and it's going to really mean unnecessary expenses when all is said and done. So the U.S. Department of Energy recognizes this, and they have, under their Solar America initiative, they have established what is known as the Solar ABCs, which is a Solar America body for codes and standards. And the objective of the Solar ABCs is to coordinate activity amongst various standards writing organizations so that they can do complementary parts of coming up with appropriate standards for the testing long-term durability, and that they would not be falling over each other and duplicating effort. So going forward, the Solar America body for codes and standards has put out a directive, and it's anticipating mainly three tracks. And in one, they're saying we need to have accelerated qualification tests. This is where tests will be done as a very minimum requirement for modules to be placed into the market. For a higher level of testing that is capable of comparing the performance of different designs, whether they're your own or your competitions, ABCs are saying you need to do testing like this as well. And one of the organizations need to take this on. Then, of course, finally, the accelerated lifetime testing, which has a goal to predict the real service life of modules placed out in the field in different locations. That is work that is also being undertaken. I'd just like to say that for the qualification tests, the Solar ABCs has deemed that the IEC 61215 and 61646 are adequate for that purpose. So that work can be considered already done. Talk about some of the work that is underway now. Now, as far as ASTM, they have taken up the call from solar ABCs, and they have in their strategic planning indicated that they need to develop accelerated lifetime testing for solar ABCs and to come up with some service life estimation protocols for outdoor durability testing as well as laboratory testing. And there's ongoing work in ASTM E44 for those who would like to join those activities. I must say that I don't think the work is moving very speedily along because they've recognized that, and when it comes down to PV testing, the IEC EC82 is really the go-to organization, and they have undertaken a lot of work to develop standards. So I'm going to spend a little bit of time talking about the activities here in IEC TC82. First of all, a personal mantra here is that we find in the PV industry, whenever weathering tests is alluded to, called for, is typically done so by the term UV test. You'll almost never hear people who have been in the industry for a long time talk about weathering tests. It's always UV testing. Now, I have a one-man campaign trying to change that, because a UV test and a weathering test are not the same. However, when they do talk about a UV test in the PV industry, they really are talking about weathering tests. In order to expedite things along, it was determined that the IEC ought to really separate activities in different materials groups. And I guess this came about because there had been a lot of activities and that amounted to basically spinning of the wheels that had taken place in the prior years. So it was determined that these materials groups should be established. The task group objectives for these individual materials groups was to identify the critical characteristics of their particular materials and develop characterization techniques for determining the materials suitable for PV applications for those materials. So the backsheets people, for example, would be looking at what are the essential qualities of the backsheets for PV modules, and how do we characterize those, and how do we determine the hazards that are associated with failure meeting those required conditions that are identified. And similarly for the adhesive groups and the encapsulant group. Now, the partial discharge, even though that's not a material, partial discharge is a big deal in the development of PV, so they were established as their own group as well. Now, directing the activities of all of these groups was a steering committee. Incidentally, it was after these materials groups were established, it was determined that, all right, we're going to be identified critical characteristics for materials being evaluated when they are new and pristine. However, we will also want to make sure that these materials are capable of meeting these criteria as they age, as they're weathered, after they've been in the field for 5, 10, 15 years. So the light bulb went over their heads that we really ought to have a weathering group that serves all of these different individual task groups looking at the different materials. So when you look at the ASTM definition of the durability, remember, we're looking at a measure of the retention of original condition and function of a material after exposure to a specified set of weathering conditions. So this is perfect definition that justifies the establishment of a weathering group to assist in the development of appropriate standards for the various EC materials groups. I, by the way, have been asked to head the weathering group, and I have been leading the activities here now for about a year and a half or so. So this is difficult to see, I'm sure, but it's available should you request a copy of this presentation. And I show this just to say that the activities of the weathering group has been divided into basically 4 streams of work. And the orange stream is to look at the standards that are out there, regardless of whether they were developed, what industry they're served in, so forth. See if any of these existing standards could possibly be used as they exist or be modified slightly for use in the PV industry. So the thinking was If we have tests that are out there that are pretty suitable, then why reinvent the wheel? So that work has been undertaken. And then go now into the next column, the green column. Actually, the green column and the purple column come under the heading of materials testing, as opposed to module testing, which is where the blue activities take place. So for the materials testing, two streams of activities. There are those in the IEC group that believe testing the materials in a PV stack that is representative of a module is the essential way to go. So that is the work that will be taking place in the green stream. The purple stream, of course, would be testing the materials by themselves, not in a stack, just in a coupon format. Now the work, the requirements, and the test methodology, and almost everything that you'd have to consider are different from the green stream to the purple stream. I'll talk a little bit more about that as I go into the reports of the groups that work that has taken place so far. Since the establishment of this layout, the blue team or stream has been adopted by another PV testing development, which I'll talk a little bit more as I go through this presentation. Now, after the establishment of the weathering group in the IEC, we were asked by the IEC TC82 chair, John Hogelmuth, to address an urgent issue. Now, the rewrite of the IEC 61730 is underway, and it has a glaring error in terms of the weathering requirement for polymeric materials. And the issues is shown here. The current wording is stated, if exposed to direct or indirect sunlight in the specified installation orientations, the material shall be resistant to weathering in accordance to ISO 4892-2 or ISO 4892-3. We're saying that this is meaningless because this statement really embodies 5 different test methods which are specifically designed for testing different materials and yield different results. Therefore, they are not interchangeable as is suggested by the wording shown above. So I was asked to provide more meaningful wording and keep the intent of what was meant in the wording itself. Being a representative of a weathering instrument manufacturer, I didn't think it was appropriate to do this by myself, so I established a little ad hoc committee. And that ad hoc committee comprised of John Hogelmuth himself, Robert Plade and Alex Bradley, myself, and Michael Cole was invited, but he was unable to attend. And our approach was, as is shown here, to address the first phrase of the existing statement, which says, if exposed to direct or indirect sunlight in the specified installation orientation, we recommend that we categorize each of the materials that we're going to be looking at in terms of the light they will see in the PV stack. Okay? So if a material is going to be subjected to direct solar radiation, we simply use the term direct. If a material is going to be subjected to transmitted solar radiation, we could say transmitted dash indirect. And if a material is going to be subjected to reflected solar radiation, we simply put that in the category of reflected indirect. So then we would categorize the following materials, all of which are used in a PV stack, either as D, red D for direct, the red I for indirect, and it could be indirect T or indirect R, or none at all. If a material is so buried into the stack that it never sees the light of day or any portion of the light of day, then we will say that there's no weathering test required for that particular material. After we've done that, we've come up with this identification and for categorization. We then have to look at the various materials that are shown here and say what kind of categorization is appropriate for them, and we'll do that going forward. After applying, therefore, that designation to the generic standard ISO 4892, which is what exists in the 61730 right now, we then say, all right, for direct, we would simply use the ISO 4892 cycle 1 at 0.35 watts per square meter. This is for materials that fall in the direct category. For materials that fall in the indirect transmitted category, we would do the same as above, but test the material in a package. Like, for example, if it requires a front glass or substrate material, then we'd apply those to the material that we're looking at and then test it just as it would be indirect. Now, for indirect reflective, it would be the same as the direct, but we would apply 15% dosage to the total test requirement to reflect the fact that if the material is only seen reflected, like for a backsheet, for example, you're typically only getting about 15% of the dosage that you would receive on the front side of the PV module. So this was what was decided on for the quick replacement of the 61730. Now, as I've stated in the box here before, it was recognized by the Adhoc Committee as well as the membership that this was put to in the IEC meeting in Montreal last year, that this is an interim recommendation, a quick fix to correct what was a glaring error, and that this would be a placeholder until more appropriate tests were developed by the individual materials groups. And the justification for this was that these test requirements that we have shown here on the left are technically equivalent to the ANSI 746C, which is the existing test method in the IEC 61730. The test method is understood to be very conservative. I, for one, thought it was too conservative, but I was there as a facilitator, not to push my agenda or my opinions. They wanted to keep something that was equivalent to what was there before, and this is equivalent. But it is a very modest test, very mild test. To continue on, that maintains the status quo, and we're using this, as I mentioned before, as a placeholder until more robust tests are developed by the group. Now back to this diagram again, because I'm going to be going into some of the specific updates on the various streams, the orange, green, purple, and so forth. As I mentioned before, the work in the orange group is complete. We surveyed all the standards out there. We organized the standards by technology, intent, and suggested how materials groups may use them. These were distributed in a spreadsheet format to everyone, including the materials group leaders, with instructions as to say, look at these, choose which ones are most appropriate for you, and select those for your testing of your materials. This did not work very well, so it became very clear to us that we have to take a more proactive approach. And I'm going to talk about that as we go forward. In the green team, where, as I mentioned, we're looking at the testing of materials in a PV stack arrangement. Even though there are many people who said this is critical, we weren't getting the help that we needed from the industry, the people who could actually define what a PV stack would be and how one would be developed in order to make sure that it is faithful to the end design of a module. There are some, by the way, who believe that this is almost impossible to do, where others claim that they are doing it and they have done it to some measure of satisfaction. At the recent National Renewable Energy Workshop, this issue came up again, and The work, by the way, I should have said, because there's so little activity, has sort of gone into dormancy. But based on the level of enthusiasm that came out at the recent workshop for this kind of testing, we've taken it out of mothball and says, okay, if you think this is so important, then you need to volunteer your expertise and your time so that we can define what a stack looks like and how we test the modules going forward. So that work is going to be rejuvenated. For the purple team, we are in the process of looking at the OrangeTeam's output. In other words, the work that was done to look at existing standards and see if they're suitable. And we're going to review these against the field data that we take for the various materials to determine what the best conditions are for, and to see whether the standards can be used verbatim or whether they need modifications. Once that has been done, we'll do some round-robin testing for validation purposes, and then for further validation, we'll use failure mode effect and analysis to test our assumptions. This is a more long-term proposition, but it will take place eventually. And why we will use failure mode effect and analysis is because we found, especially in our consultancy group, that this is a very effective way to establish a bottom-up materials design, or you determine the role of specific material chemistries. It's useful for planning environmental durability tests, and it can be used to determine the suitability of test methods. But this is really the point that we're going to be exercising. And when we do that, we recognize the fact that we will never have absolute certainty. On this arrow, this big dark arrow here that looks at the continuum from absolute certainty to pure guess, we will be operating closer to the absolute certainty, but not entirely over at the end of the spectrum here. We'll be using our experience, and we use theoretical understanding, and we will use FMEA to test whether we have come close enough to where we want to operate. Going forward, the OrangeTeam work is going to be looked at by the purple team, and we're going to, just as we did in the original case for the 61730 effort, we'll be doing this for the individuals materials groups. I mentioned we're going to take a more direct and proactive approach with the materials group. Here's one case of that, where we've done this already with the backsheets people. The first thing, of course, you have to do is to characterize your various materials that have task groups in the same way that we decided how to categorize materials for 61730. So the backsheets, I'm told, would be in a indirect reflected. Obviously, you're just going to get reflected light from the back. Adhesives would fall in all category: direct, indirect transmitted, and indirect reflectance. Encapsulants, the same thing. Edge sealants, direct and indirect transmitted. You use that as a guide, determine what test methods would be appropriate. Now, once you've done that categorization, you want to have test conditions that are meaningful but are as extreme as possible, so you can have some acceleration. And it was determined that we would use our data from our benchmark facilities of Florida and Arizona and come up with two extreme cycles to test each material. The extreme cycles would be hot and humid and hot and arid. Now, others are being pondered, but right now the ones that I've shown here are the ones that we will focus on. So, to continue on with the backsheet materials as an example, we're going to be using the hot humid conditions here in this example, and so we need to identify the typical conditions that make up the hot, humid conditions for a backsheet material. And the conditions that you have to identify are the appropriate relative humidity, temperature, irradiance, and spectral power distribution, and whether there's to be cycling or not. The relative humidity is we selected were very high. Again, we wanted to go as high as possible but realistic. 50% in the light when the light is on and 100% in the dark. And that is so because in Florida, for example, there's dew formed every single morning that the sun comes up. For temperature, we selected a 65C. That is harsh but not unrealistic. For the spectral power distribution, I'll defer that until the next graph. And for the radiance level, we wanted to have 30%. Again, the reason for that will become clearer on the next graph. We talked about characterizing the environment for each material. Michael Cole from the front office ISA has begun to do that for the backsheet materials. And you can see here that he's actually taken spectral power distribution measurements in a number of different ways on the back of PV modules. He's taking it parallel to the PV module, and he's taking the measurements perpendicular to the ground. And the spectral power distributions shown here in the graph suggests that in the back of the PV module, you're getting about between 15 and 30% of the radiation that you would see on the front. But it's also important to note that the spectral power distribution doesn't change. In other words, you're getting output from all of the wavelengths on the back that you would the front, just at a reduced level. So using those two pieces of information, we say then it's appropriate to use the spectral power distribution for daylight, which is what I'm showing here. And for the front sheet, you have 0.7 watts per square meter. That's a peak. If we're going to use for the backsheet material, you use between either 15% or 30%. 15% is where the average measurement took place, but if you really wanted some acceleration, you could justify going up to 30%, as some of the measurements that he took perpendicular to the ground were up to 30%. I mentioned before that we already have the 50% relative humidity, the chamber temperature of 65, and the black standard would be 100, BPT would be 89 in order to achieve the chamber temperature of 65. Now the open questions to complete the test method for backsheet are shown in red here. What would be the test duration? Is cycling considered important? Do you need to have a light on and a light off and a water spray? And based on the feedback that I recently received from the backsheet people, it's yes to all of the above. They do need cycling, and they do need water spray, and they do need light and dark cycles. And the test duration is to be determined. Now going forward, we're going to duplicate this exercise with all of the different materials groups in order to come up with some proposed test methods for them. And the ISO 4892 will be used as the baseline standard to modify as we see fit for each group. So that's it for the great bit of activity that's taking place in IEC. I will quickly go through what's going on in some of the other standards world. For some time now, UL 1703, which is PV modules and panels testing for safety, there's been an effort to combine, harmonize the 61730 from IEC and the UL 1703. The sticking point has been the use of the RTI, Relative Thermal Index tests for UL. UL believes that this test is very viable. The IEC, which is an international group including the Europeans, will not accept the RTI. So the negotiation continues, and we believe that the work that is being done that I just described before in the materials groups for IEC will lead to a path around this logjam. Another significant activity that's taken place is there's been a development of an international PV module quality assurance forum, And this has been led by the National Renewable Energy Lab and the AST of Japan. And their whole objective, as I say here, is to combine the best features of the existing methodologies for testing PV modules out there into one amalgamation of a test that everyone can use. I think this is a very tall order myself, and I think so because the tests are so fundamentally different. However, the activity is ongoing, and if you should have an interest in taking part in this, you can contact me or go to the website that was shown on the previous slide. In the very recent NREL workshop that took place, all of the owners of the various test methods that are being used today for module testing were asked to give a brief overview of what made their methodology different from the others being offered. What were the standout features of their methodology to see, to show if to the entire set of participants so that a decision could be made going forward as what features could be adapted and whatnot. When we presented, we said that what distinguishes our method from others is that we adhere to the first principles of weather and test development, and those are shown here. That the test method must be accelerated to get answers as quickly as possible, must be realistic, must correlate to something, it must employ the same stress factors and failure modes that you see in real life. It must be relevant, it must produce the chemical degradation mechanisms that we see in real life. And in order to do that, it must have the real weathering stresses applied simultaneously. And we believe that it needs to be precise enough so that it can be repeated from time period to time period. And it must be also comprehensive so that all the relevant failure mechanisms can be reproduced. So these were the points that we attached to the presentation of our Atlas 25 test program. So there's a lot swirling around. We have presented a lot in speech fashion, and your head may be swirling a little bit, and so let's see how we can make sense of this. So it's a given now that the renewable energy market is moving from research, government funded, and so forth into real businesses. The government incentives are going away. Solar businesses are forced to operate in the classic business style, which means it has to make money. You have to do that, you have to control your costs and manage your risks. PV business managers are going to be looking to their technical staff for sound durability and reliability analyses and assessment of service life estimations to estimate warranty exposure and so forth. When they do that, they're looking to you for speed and accuracy. Speed to facilitate the fast business cycles, and accuracy, of course, to minimize any sort of liability exposures so that they can mitigate risks associated with the poor product quality that I talked about at the beginning of this talk. To do that, yes, you have to utilize standards, but as I mentioned before, and as you probably already know, the development of consensus standards take a very long time. While you are waiting for the development of these standards, you may have to do things on your own, and you may have to employ some out-of-the-box thinking. You may have to do some customization. By customization, I'll give you an example of that. Mike Kempe from National Renewable Energy Lab developed an accelerated UV test. Again, it's an accelerated weathering test and selection criteria for encapsulants of PV materials. And he did this because as he pointed out here, the current qualification tests are not good enough. They do not require UV exposures that were high enough to evaluate a 20-year lifespan. So he needed to adapt existing test methods for the to develop a method that was suitably fast for looking at the encapsulant materials. And he's done this fairly successfully, and the paper that he's produced from that work is available from Atlas as well as from Mike Kempe. Some more out-of-the-box thinking. Atlas has in its solar test facility an ultra-accelerated exposure device that's capable of testing materials at many times the sun level. This is not a commercial, this is just an example of what can be done to for out-of-the-box thinking. Utilize, being creative to do things that will get you test methods faster and get you test results faster than having to wait for the development of consensus standards. So, going forward, we recommend that you prepare to meet the demands in these various ways, and they're not mutually exclusive. Yes, I think there is value in becoming active in the development of consensus standards. The collegiate exchange of information is invaluable. And if you want standards that will be relevant to your product and your business, then you have to have a seat at the table. So contribute to the development of these standards. You can get your philosophies incorporated, and you can get more relevant test standards in the end. The process is slow, and you may want to do something on your own, as I mentioned before. While doing that, you must remember that weathering is a very specific, specialized discipline within a more broader discipline of durability and reliability. You may have some expertise as well, but don't necessarily look to reinvent the wheel. Seek help where it exists or where you need it. We suggest that you become educated on the subject of weathering in numerous ways. There are many, many great publications out there and a lot of expertise. You should conduct a clear-eyed assessment of whether you can go this alone, look at your in-house capabilities, and if you need help, there is a lot of help available. You can purchase expertise, and you can at the same time develop your own in-house capabilities. But whatever you do, it's becoming a very competitive market space. Get on board and start now. And with that, I will end my presentation today. And this is my contact information. If you should need to contact me for a copy of the presentation, please do. Or if you have any input to what I've said here, I invite you to send them to my email address. Thank you very much.